My name is Louisa Smieska, and I'm a staff scientist here at CHESS. FMB stands for the Functional Materials Beamline, and when we talk about functional materials, we're talking about things that have interesting non-mechanical properties, so things like semiconductors or nanoparticles. In reality, at FMB, the distinction between functional and structural materials that we study is a little bit more soft. We actually study a lot of structural materials here at FMB. In particular, we tend to look at lighter weight materials that are more compatible with the energies we have here and not with our sister beamline at SMB, where they study heavier things like metals. So FMB is part of MSNC, which is funded by the Air Force. The Air Force Research Lab is really interested in next generation materials, both in discovering those new materials and translating new materials into industrial processes. And we do that by characterizing materials at the microscale and at the macro scale, from millimeters to even greater length scales. When I think about the capabilities at FMB, I think about flexibility. We have kind of 4 areas that I consider really flexible and kind of are what make the beamline unique. And those are the energies. We've got 4 different energies, and we can hop between them kind of at will. This is distinct to a lot of the other beamlines where changing energy is kind of a big task. We have really flexible optics, so we can go between having a big beam that's 2 by 2 millimeters down to a focus beam of just a couple of microns. So that allows us a lot of flexibility in how big a piece of the sample we illuminate. We have a really flexible sample area, so we can have users who bring in really complicated in situ setups, and we can build up everything to lasers and robot arms all the way down to micro focus sample stages. And then the last piece that is really flexible is the detector table, so we can use that to change between our different experiment modes. And so the 2 main experiment modes that we have at FMB are imaging, and that's similar to what you'd imagine for radiography at a dentist or at the doctor. So there you're taking your big beam, your 2 by 2 millimeter beam, and you're taking movies of dynamic processes, or you're taking computed tomography, so 3D reconstructions of objects. So that's one mode that we have. The other mode that we have is scattering mode, and that's typically we do simultaneous wide and small angle scattering, so simultaneous wax and sax, or sax wax, people say both. The idea there is that the scattering is going to tell you about the length scales in your sample. So wide angle scattering will tell you about the really small length scales, so interatomic spacings. It helps you understand crystalline materials. And then the small angle scattering tells you about the larger distances in your sample. And that's useful when you have things that aren't quite as crystalline, like the polymers and composites that we look at here at FMB quite a lot. So everyone's probably familiar with the concept of 3D printing or additive manufacturing, where you kind of print one line of material and go back and forth, and you can build up a complicated part. The properties of those things are maybe not so important if you're just printing a toy, but they're really important, and the reliability of those parts is really important if you're doing something like driving a car or putting it in an airplane. Our role at FMB in understanding 3D printing is to look at both the in situ processes as they're happening on the beamline, or we can look at ex situ parts that have already been printed, and we can characterize those and look at their structural properties. Right, so I also mentioned that AFRL is really interested in discovering new materials, and so one piece of what we do at FMB is support groups who are interested in automating materials discovery, and they do this in numerous ways. We've had groups bring solution mixing robots to the beamline, where they've actually combined different solutions and looked at their properties kind of as they're being created. We've also had groups bring a complicated kind of laser annealing setup. So they've got a wafer with a bunch of different oxide materials on it, and they're actually annealing those oxides in situ and looking at the diffraction patterns to know what crystalline phases are present. And the goal of that experiment is to actually have a computer across campus decide where to look on the wafer for the next compositions and decide what annealing conditions to use to explore the wafer and basically come up with new phase diagrams. So that's really exciting work. So remote access has been going really well, and one of the reasons it's been so successful is that our standard SAX wax mode that I mentioned is really compatible with remote and kind of mail-in operation. So we've designed these special sample holders. We can send them to users, they can fill them with their samples and send them back to us, and it's really easy for anybody to just attach this sample holder to the right mount and pop it on the beamline. It goes into place with a kinematic mount, so we know exactly where it's going to be. It's going to wind up in the same place every time. You don't have to have special training to mount the samples or to prepare them in your lab to put them on the beamline. So that has worked out really well. Not only can the user log into the station computer to collect data, but they can actually also log into our analysis computer at the same time. And so they can be collecting data and running scans and also looking at the process data as it's being collected, almost as if they're sitting right here at the beamline. Right, so I talked a lot about the Air Force Research Lab and collaborations with DoD, but a lot of these research questions that we're studying, particularly with the 3D printing of lighter weight materials, are really relevant to everybody. And you can imagine that lighter weight components for aircraft are not only valuable to the Air Force, but would also be valuable for commercial airlines, particularly through the avenue of reducing fuel use or improving fuel efficiency by having lighter weight components. So you can also think about the ease of manufacturing. If it's possible to make components, replacement components for aircraft while they are away from a base, so maybe somewhere at sea, or maybe we're talking about like spacecraft, maybe you're printing parts in a space station, you need to be able to do so reliably and consistently. So I think that's really cool. Yeah. Yeah, so we're a pretty brand new beamline. We're only, I guess, a year and a half old at this point. And so there's a lot of areas that we're still growing into. And the main areas that I'm thinking about are, improvements that we can make to the techniques, and improvements that we can make to access to those techniques, and also expanding our user base in AFRL and DoD and the related manufacturers. Most of our efforts over the past year and a half have been towards really improving our techniques and making them excellent. And now the next step is to make them even easier to use. I think our biggest efforts now are going to be towards streamlining transitions between all these different flexible components. And we've already made some improvements, like being able to translate our detector table from side to side. So now switching between SAX wax and 2D imaging is a simple one motor move. The entire table slides over and you can have your in situ setup right there on the table in the same place. The beam is in the same place, and all you've done is change the experiment around it. So there's a lot more, there are other things like that we'd like to implement, like improving our camera views of the sample, which will also help people who are operating remotely and things like that. But yeah, we're sort of shifting from technical improvements to ease of access. So one of my favorite parts about working with AFRL and all of the chess researchers that are part of the team is that it is such a great team. Everybody's really invested in solving these materials problems, and we work together really well. And it's a really collegial environment, and the people are terrific. Yeah.